Hi, folks. Stephanie Camp and I nominated Dr. Antonio Meira for this talk. Antonio joined the faculty here in the fall of 2023, but I actually ran into him at a conference before then. And I was really excited to hear that he was coming at this conference because of his enthusiasm to discuss hydrology. As you all know, hydrologic analysis is sort of spread across our campus. And so Antonio's in the civil and environmental engineering department, but the way sort of he approaches the question of large scale hydrologic analysis, I find really interesting and exciting, and I'm excited for him to share this here. Antonio did his undergraduate and master's degree work in his native land of Brazil, and then he did his PhD at the University of Arizona, and then after that popped back and forth from Brazil and the US, but has landed here. And I think this is just the end of your second semester, right?
Yep.
Yeah, so fresh. So please join me in welcoming Antonio, and you'll take it away.
Hi, everybody. Thanks, Matt, for introducing me. I'm very excited to be here. You know, for if it serves as a advice, you know, I went through a postdoc in Brazil. I was unemployed for a year. I mean, talking about the graduate students, right, who want to go at academia. And I was unemployed for a year during the pandemic, working with collaborations that I established during my PhD through my networking and so on, and ended up being a very productive and stressful time. Stressful because of pandemic and job uncertainty, but productive for sure. So came back to the United States, did a quick postdoc. I taught in a teaching institution for 1 year, and here I am at CSU. So sometimes we have the impression, and I don't even know if you guys want to follow academia or not. I'm just giving advice that maybe be useful or not. But sometimes we think to become like faculty in an institution, very good like CSU, you got to be following a very linear path. And my example, not to mention I come from Brazil, from a very small college in my undergrad, hopefully serves as an example that not everything has to be in a certain way. But going to my talk today, I'm very happy to be here. Happy to see Matt, Stephanie, Carol, and some other people that I don't know. This is a result, funny enough, of part of this time that I was in Brazil, that I was stuck and I had to collaborate. And it's a project that started in 2021 that I could do a little bit here and there, and it's been going on until now. And I think we're coming to a point where we can finally publish it. And I think the topic here is something that might interest you, right? Hydrologic analysis, like Matt says. So let's go over what's the main motivation of this type of research, not just my research? It's variability, hydrologic variability. So what I mean by hydrologic variability, if you think of variability, very broad scientific definition, we can talk about space or time. And I get this example here, it's very basic, right? The mean annual precipitation on the the mean annual precipitation on the x-axis and the mean annual runoff for 671 catchments in the United States. And each point here is the average of a catchment. So this is what I call spatial variability. How things vary in space, how catchments respond in space to the same input, precipitation. Or you can think of time. If I pick one of these catchments here, still learning how to use this. If I pick one of these catchments here, and I now plot each year the same relationship, precipitation and stream flow, you're going to see a different type of variability. And there's definitely a similarity, as you can see, comparing both figures, right? So variability is the main motivation for this type of work. What explains, literally, the spread, the shapes of these relationships between, for example, precipitation and stream flow. We can talk about variability of many other hydrologic signatures. But Now, again, we have each dot here becoming a year, not a catchment. So the main, the driving question for this work is what you see here. How does climate variability at different time scales manifest in hydrologic signatures? And this is it's a picture from a famous paper, very known paper on spatial scaling, where the authors try to come up with a theory on how things scale in space, not in time. And the motivation, the reason why we believe this type of work is interesting, well, the hydrologic processes that drive the signatures are intrinsically variable, right? And the spatial variability of catchment physical properties helps explain the variability of hydrologic signature. So there's a part of the variability you saw in those previous figures that comes from differences in space, properties of each catchment. You can think of soil depth, porosity, the type of the bedrock, and so on. But the spatial variability of these signatures can also come from the spatial variability of their climatic drivers. So we're talking about the y-axis here, right? So hydrologic processes occur both in space and time, and we're interested in understanding this y-axis here. What is the time variability driving variability of hydrologic signatures? So in the, why we did this, there's no comprehensive theory in hydrologic scaling of temporal processes, right? So someone has just, it would be good if someone or a group of people sit down and try to think how things connect, what makes sense. Why should you care about temporal variability, right? Or climatic variability? Well, climate change is one. And as we know, climate change assessments, climate change prediction rely on many, many models. And models you can think of simply as assumptions, right? Or a collective of assumptions. And we do have many models, but we have many gaps in theory. You can run a model, but you can have a given response. But if you ask me how universal is that response from that given model, I don't know. So there are many gaps in hydrologic theory, something that, let's say, goes beyond a model, one single model, right? So what are these gaps? And this has a little bit to do with what we're gonna see today. For example, seasonality and water yield, right? Seasonality here for this presentation is how the cycles of monthly potential evapotranspiration, which are the two solid lines, interact with the cycles of monthly precipitation. So you can see two different modalities of seasonality. One of them, precipitation, is in phase with potential evapotranspiration, meaning this guy here. The other one is what we call out of phase. So it rains more when it's colder versus it rains more when it's warm, if you think of very simply ways of thinking about that. Another gap is how climate variability that we're interested in discussing have to do with the long-term partitioning. Long-term partitioning is normally addressed as typically, you can think of it as a Boudico plot. Phi is the aridity. E over P is the fraction of precipitation that becomes evaporation. And normally you could see, like, for example, a point meaning a catchment or one specific year of data. And these points tend to collapse or aggregate around certain regions or move across the space of this plot due to some changes over time. So this is a type of variability that might be benefited if you think of how temporal processes scale in time. Other type of variability on extreme events, for example, a typical hydrologic signature, the flood frequency curve, right? We have the return periods on the x-axis is the maximal annual flow of a given year plotted on the y-axis, and you can see a shape of a curve. So what types of climatic controls determine the shape of this relationship? That could be something we can gain from a better understanding of temporal scaling of climate. Another type of signature we're going to see today is the stream flow permanence. This is a flow duration curve. Another very common
catchment descriptor, hydrologic descriptor that relates the stream flow on a given magnitude of stream flow versus a percentage time of exceedance. For example, if you have a point here with 40.4 means 40%, that means 40% of the time stream flow is greater or equal to some value on the y-axis. So it's a type of signature that collapses a lot of information into one single plot that lets you learn a lot about the behavior of a given watershed. Again, a type of signature that we don't really understand really well what are the main controls, especially in terms of temporal processes, right? And interannual variability, again, the plot I showed in the first figure, how precipitation in different years relates with stream flow on different years. What drives this pattern of this curve? What drives the variability around a given mean? So what have we done, right? So we focused first on a broad literature review. Our literature review encompassed mainly large sample hydrology studies, not necessarily modeling studies. We got empirical, analytical studies that use actual data from a variety, from large data sets of catchments. We did some literature review, mainly on these empirical studies. We did look at modeling studies trying to address these variabilities we're going to talk about, but only if those modeling studies were trying to answer these questions. And we tried then to synthesize these findings. I'm just going to put my timer here so I don't go to. I want to get lost. Okay. So what's a common thread, right? And that's where we start the presentation, right? This very simple conception framework we came together with. This is simply a series of precipitation events. That's on the y-axis, the precipitation intensity. Each event has a given duration. You see multiple events here. And there's a time between events that basically separates those events, right? TB and TR. Why is that important? It's because at the event time scale is the time scale where hydrologic processes happen, right? Evaporation happens minute by minute or day by day, stream flow formation and so on. So you can think of while precipitation is falling, a few things can happen, right? You can have some quick flow being formed, what I'm calling F or fast flow, some infiltration, some slow flow being released, and a change in storage being positive. In this time, where you don't have precipitation, that infiltrated water might become evapotranspiration or might recharge the underlying aquifer. There is a negative change in the storage in the unsaturated zone and a positive change in storage in the saturated zone. So if you think of those same properties I showed for one event, what are they? The duration, the between storm period, and the intensity. And if you think about a given year, duration, between storm events, between storm time period, and intensity will vary according to some pattern. We don't know, just writing down some different realization of that. And what we have now as our monthly cycles of precipitation, these are possible realizations of monthly precipitation, is nothing but a transformation of these properties. And this is just a simple math to, if you do the math of what one event is versus a whole month, will be this formula here. So these storm properties scale up in time according to this function, giving rise to some monthly precipitation. On top of that, we have some realization of climate, in this case, with the potential evapotranspiration, which drives the hydrologic cycle, that it's superimposed with this variability in precipitation. And lastly, this variability can be then tracked in terms of storage and stream flow components, fast flow and slow flow. Storage, for example, unsaturated zone, saturated zone storage. So the main idea here is that this variability propagates and ends up being represented as fluxes and storage. Now, if you think of not 1 year and think about many years following each other, you would have a similar pattern in which different variabilities might happen in different years, giving rise to annual timescale patterns of those variables in their means. The average annual rainfall duration, average annual between storm period, average annual intensity, and so on. And that is related to annual precipitation, annual stream flow, and annual storage. And that makes you thinking of all this variability, you know, does 1,000 millimeters of rain is the same. So if you have 1 year, let's say those two columns are the same, they might have the same annual precipitation, but were they generated by the same average intensity, average duration? We don't know unless we start to investigate that. And that's what we think of, you know, finally arising as some sort of variability here, and I'm showing the interannual variability of that curve, precipitation stream flow. So in this, you know, I'm not going to go over this slide too much, but we came up with, okay, what is the water balance equation that makes sense for each time scale? What are the terms of the water balance equation that can be dropped or that cannot be forgotten for a specific time scale of interest? So we have the event and the recession time scale, the seasonal time scale, the monthly time scale. We have the annual time scale and the long-term mean. And you can see the water balance equation has different components that are more or less important. Now, I'm not gonna go spend so much time on this, but the signatures we're gonna explore are related to, some of the ones I'm gonna show today are related to different time scales. So before I start, you know, showing the results, what did we do? Even though our study is about trying to explain empirical patterns, we're doing modeling here as a hypothesis testing. We're using models to drive hypotheses and ask questions, right? Not necessarily to represent a specific catchment, but we're using a very simple hydrologic model. You don't have to look at the equation so much, but look at this here. It's a bucket type model, right? There is a bucket for soil, a bucket for the saturated zone. Precipitation is partitioned. There's some function that transforms the soil water into evaporation or recharge. That recharge then is released as a slow flow, base flow, if you will. And there's also a fast flow component. So this type of model is shown to, you know, I cannot show you the slides proving that, but it's a type of model that can represent well many watersheds in the world. It carries with it the main hydrologic processes, or at least their description, in a way that you can reproduce the behavior of any, I would say most watersheds, except if you're talking about snow. Snowy catchments are not, but we can do a simpler model for snowy catchments as well. So what we coupled with this simple hydrologic model was a simple stochastic rainfall model. Stochastic rainfall model is a model that I can use to generate artificial series of precipitation. And because we're interested in controlling some of these features, so we follow the stochastic model that has the variables that we are interested in, right? The between rainfalls period, the duration of a rainfall event, the average intensity, and so on over time. Just for curiosity, the between rainfall and the duration are exponential probability distributions. Exponential distribution only use the mean, so delta and gamma are means. And these means vary seasonally. So it's a funny function. These are just to say that the means that we use for generating this between rainfall and the rainfall duration, they vary over the year according to some mean that goes from low to high, and we can control that and generate different climates based on that. And the intensity is not shown here, but it's a very similar concept, but it's a gamma distribution. Gamma is two-parameter function, right? Mean and variance, not just mean like exponential. So, and then, you know, we have this rainfall model, we have stochastic model. So let's start looking at this research we've done, the literature review, and trying to find questions that might benefit. And I'm bringing one in, for example, here. So how does seasonality modulate the water balance, right? Seasonality, again, the mismatch or the match between potential evapotranspiration and precipitation. So, and there are many papers trying to address this topic since the early 90s to last year that tried to give an answer to this, I would say, very long-standing question in catchment hydrology. So is there a definitive answer? And if there is, what is the answer that can tell you, on an elevator pitch, what seasonality does to the water balance? And this is a figure from this paper from 2007 that shows how catchments that, let me just go one thing here. Before I go to this figure, most papers until recently assume that when rainfall is in phase with potential evapotranspiration, you have more evaporation than runoff. If the opposite occurs, you have more runoff than evaporation. But there's some mismatching results that are poorly explained that people seem to choose to ignore. For example, Australian catchments in which the opposite occurs. This figure is kind of convoluted, but basically for the Australian case, catchments that are out of phase, meaning there's a mismatch between potential evaporation and precipitation, they tend to have more evapotranspiration than catchments that are in phase. So that was something that motivated us. So what might explain that? So one thing we're going to do first with this model is to generate one precipitation time series in dashed black line and two seasonal cycles of potential evapotranspiration, right? One is in phase, the purple, out of phase in red. And let's just go figure by figure. So this is a result that is typical, right? When you move from in phase to out of phase, you go from higher evaporation to lower, meaning you're producing more runoff when you go from in phase to out of phase. And you can explore these results by looking at these model outputs, but I just wanted you to look at how this shift between in phase to out of phase, in phase being purple, out of phase being red, favors recharge. Similar, these are infiltration access, fast flow, and favors recharge for the case of the red line. Okay. So let's focus on this figure now. So when you go from in phase to out of phase, you produce more runoff. So that's cool, but we want to explain, we wanted to explore further, what if your catchment is in phase, but something else changes, right? So we generated two different time series of precipitation. And we were very careful to make the means the same and have two time series with the same seasonal cycle of precipitation. Same seasonal cycle, same average precipitation, meaning they have the same aridity. But one time series has a long storms in summer versus very short storms in the summer, low intensity in the summer, high intensity. So this series one has long, very mellow storms in the summer. This one has short bursts of high intensity rain, although both of them have the same seasonal cycle of precipitation. We wanted to explore what that causes in terms of partitioning. And this is the result. Let's look at the first one here. So for the same cycle in phase, differences in storm properties may give you a result such as this one. You're producing more runoff on simulation number 2. Simulation number 2, again, intense storms in the summer. So that's something that has not been fully explored. Besides simply monthly totals, what else might drive long-term water balance partition? And you can see the results here. Simulation number 2 has less recharge, less ET, and a bunch of fast flow, a bunch of, you can think of it as infiltration excess, but in a realistic case, you would have infiltration excess, saturation excess, overland flow as well. So that's a pattern that can be seen as resulting from a timescale property of that storm, timescale patterns of those storm properties, right? You can think about comparing those two types of simulations, aside from their long-term means, in terms of the variability of the relationship between precipitation and stream flow. Series number 2 has slightly more runoff being produced. They, again here, the Budico type plot where we show each circle representing a year, where this precipitation number 2 tends to fall a little bit below the purple line. This is not a super interesting figure, but this one is very interesting. The flow duration curve, and we split the flow duration curve between the actual flow duration curve, as we know, the flow duration curve of the slow flow or the base flow, and the flow duration curve of the fast flow. So what's happening here, simulation number 2 tends to have less stream flow for permanences up to, say, 10%. And this happens across slow flow and fast flow, except for the fast flow. Simulation number 2 has much more intense storms, meaning for example, a 10% return permanence, you would have much higher stream flows for the simulation number 2. So it's winning, simulation number 2 is winning against simulation number 1 in terms of their extreme events. And you can see that the patterns that I showed here, you can easily see that in terms of flood frequency curves. So simulation number 2 has much strong, large magnitude floods. So let's go again and continue revisiting this in phase versus out of phase. And we created the time series, we're gonna call it time series number 3, that again has the same mean, annual mean, as both simulation 1 and 2, but instead of following the same seasonal cycle, it peaks higher. So it's still in phase with the climate, it's raining a lot in the summer, but it's not as well distributed as the 1 and 2. And again, we can trace this back to the duration of the events. These durations are shorter and the intensities are much larger, but we're concentrating most of the rainfall on fewer months. And again, similar patterns arise, more runoff being produced, same annual precipitation, but more runoff being produced. Again, what's causing that distribution? Recharge is higher and infiltration excess is higher. In this case, we have both recharge and infiltration excess, kind of tilting the balance towards more stream flow. Now, that was just a little bit on long-term partition, right? Now let's think of exploring one of these precipitation time series, and I'm picking a precipitation time series number 2, one of those 3, and we look at the interannual variability. What I'm plotting here is the interannual variability of evaporation over precipitation, stream flow over precipitation. You can forget about this figure here and just focus on the last 3. It's easier. So stream flow over precip, quick flow over precip, base flow over precip, all for the same aridity ranges. See some patterns occur here. These curves don't seem to be random. In fact, someone may explore these patterns before and created some analytical functions that can be used to fit, and they kind of make sense, broadly speaking, physically speaking as well. And we can work on and fit some of these functions for the patterns we see. And then we can start some exploration on the variability we're talking about. So, and the example I'm going to do now only on those 2 variabilities here. The variability of the fraction of precipitation that becomes quick flow versus the aridity, and the variability of the fraction of precipitation that becomes base flow versus aridity again. So we have functions that we've fitted, F1 and F2, and we're going to see what happens. So base flow fraction, and I'm going to look especially on the catchments that are that plot above the curve. So these catchments have a, sorry, not catchments, going back. I'm used to doing this analysis for catchment amount of time. So each dot is a year. We have different years plotting above the mean, right? And these years are depicted here in gray, and the mean of all these years coming from this pattern here are also shown in the black line. And we can see what's common between them. So again, what we have here is the cluster that were formed from this choice of points here. We have the intensity, duration, depth, between rainfall period and the number of events per month. Covariance term, we have to, we would have to talk for a little bit longer to make sense of that, but it's not a very important term for this part of the talk. So what we see here, I just want you to look at this, right? So we have a given pattern of intensity and duration for the catchments that have more base flow for the same aridity. Now, if we look at the catchments have less base flow fraction for the same aridity, we have a different cluster of catchments with different rainfall properties. And it's kind of hard to see here, but intensity tends to be larger on the second group and duration tends to be smaller if you compare both subplots here. So the same patterns of storm properties seem to also be controlling the variability between different years for this given catchment. And you can think about the same figure now for the fraction of precipitation that becomes quick flow. The quick flow fraction, again, we can highlight these catchments that have higher quick flow fraction for the same aridity, look at their properties, and again, intensity and duration. Let's see how they compare. We have the quick flow fraction, catchments that plot below the curve, same, I'm plotting here, they're all the years, sorry, I keep saying catchment, they're years, each of these lines are different years from the same catchment. And we can see for these years, the distribution between intensity and duration. And here you see clear differences in intensity, being years with higher intensity in the summer tend to produce more quick flow versus years with lower intensity that plot below the curve. So again, storm properties and their variability seem to be exerting a lot of control on the interannual variability of these signatures. And if we think now of what I've just done, fitting these curves for one precipitation time series, and I do this for all precipitation time series for both runoff fraction, base flow fraction, quick flow fraction, we can also try to understand the variability in the shapes of these curves arising again from storm properties. All of these time series of precipitation have the same mean, the same interannual variability, the same spread. If you look at all of them together, you would say, oh, these are all the same year. Oh, these are all coming from the same distribution. They all have the same annual average range and mean of annual precipitation, but they lead to very different patterns in how aridity and these stream flow, base flow, and quick flow fraction are depicted. So now we can think of sensitivities to change in seasonality. What I mean by that, each of these precipitation time series, I will run the model with the in-phase versus out-of-phase seasonality. Precipitation series number 1, series number 2, precipitation series number 3, and we'll see what comes out of it. So as you expect, going from in-phase to out-of-phase, you produce a vertical shift towards producing more stream flow for all of them, but the magnitude of this change is not the same. So there's a variability, and if you think of this as a broad indication of climate sensitivity or sensitivity to seasonality variations in the climate, how catchments might respond to that, all these responses here come from the same change in seasonality, catchment with the same annual mean precipitation, but because of their storm properties are different, we have very different changes in partitioning, with the largest change being from precipitation series number 1. Again, precipitation series number 1, mild storms, very long storms. So water enters the soil and has more time to be evaporated. If you compare that to simulations 2 and 3, these are very strong bursts. So much of this water is quickly released to the stream flow. It does not become available for evaporation. Therefore, a shift in seasonality, if you think of, takes advantage of precipitation series number 1 much more than the other ones. There's water to be evaporated. Now, think of the similar type of exercise. So the previous exercise we explored here is sensitivity to changes in seasonality. Again, thinking about climate change, right? Seasonality of many catchments might change. The precipitation regime might change, so there could be ones in phase, they become more out of phase and so on. So this type of analysis helps us understanding the patterns that might happen in the future more. Now we think about increasing aridity, or simply increasing the mean of your annual potential evapotranspiration. So what that might cause. And we have for the in-phase precipitation and potential evapotranspiration, again, similar patterns all of these catchments will experience a with an increase in aridity, right? When increase in the x-axis, you tend to evaporate more, but the patterns are different, right? So there are catchments that will increase more and catchments that will increase less its evaporative fraction. Again, precipitation number one, I'm unfortunately plotting in the middle, this should be on the left, is that precipitation time series that have mild storms. So increasing aridity might create a larger shift in water balance partitioning for those catchments with very mild storms in comparison to those catchments that rely on precipitation in very intense events. And you can produce the same type of sensitivity analysis to aridity if you instead plot your plot following the assumption of outer faces analysis. So you can start to also see some patterns. The deltas here for the outer faces analysis are higher for all the models. So for all the precipitation time series, just because one of the examples have in phase or out of phases analysis, and we can, discuss a little bit of these results. But I think I went really fast. This is still work in progress. We're going to continue for the next few months, but these are just some exciting results I thought about bringing here. Our temporary conclusions are mainly that we believe to be able to show some valuable insights on how climate variability propagates across timescales. The main take home is that information from storm property cannot be lost. So when we do analysis of annual water balance, if you only take into consideration annual precipitation, you might not be telling the whole story. If you do analysis of seasonality without considering the storm properties of your catchment in question, you might not be able to depict the full story about what changes might occur in the future. And of course, the way this information propagates is a function of location, right? Each site might be different. Think about sites as, we picked a model configuration, a given set of parameters, right? And we ran this different precipitation time series, but you could have a different catchment on a different location with a different soil depth, with different infiltration capacity for the soil. And lastly, but you can think of, okay, these results might vary across site. They might be daunting, right? Well, we'll never have a universal answer for any hydrologic problem. But the fact that the climate variability is also a driver of the coevolution between soils and vegetation might offer a hint on how to solve both problems at the same time, right? So same thing, infiltration capacity, soil depth are not random functions. They follow certain climatic patterns. So we hope to find some linkages between this timescale propagation and also the variability across space through some sort of common framework that considers also how these catchment properties respond to climate. In this case, of course, long-term climate, many millennia of coevolution of climates and soils, climate, and vegetation, and so on. Yeah, that's the end of my presentation.
So just curious, so you sort of built this modeling framework for hypothesis testing. Have you applied some of those analyses to like the camels data or caravan since you have more variability in caravan? Camels and caravan are ridiculous names that I like for large unified hydrologic data sets that started in the US in 2015, but now caravan is doing it across all these other countries like Great Britain and Peru, and it provides like the sort of empirical opportunity to do what you did in modeling stochastic range.
Yeah. So all of these ranges, yes, I have in my computer always camels US, camels Australia, because it's one of the things that intrigued me. All these variabilities are within the range of all these catchments, and a lot of these, my starting point for modeling this model was some watershed in the US. So these are all
realistic values of intensity, duration, frequency, and number of events, and so on. And but so far the idea is to drive insights from this for this model to motivate hypothesis testing by other people, right? Also based on empirical results from other people, from others, such as the paper from 2007 in Australia. They show some contrasting results to what until nowadays still hold as the answer for a given problem that has not been super explored. And some other things we've shown here are within, I would say within the range of some realistic, what a catchment would be somewhere in the US, for example.
So what I'm thinking about kind of applications of this, and one thing that occurs to me is that when we try to predict hydrologic futures, we're drawing from climate models, which generally can't represent precipitation very well, and certainly can't represent it at the storm timescale. And so what do your results imply about our ability to predict hydrologic futures?
Yeah, I think that's a great question. Okay, for one point, one of the take homes is that event scale within month, within month, like less than 30 days variability plays an important role. Right? And we want to, show the full picture later on, but our hope is to highlight that. In terms of application, you can think, applying this to the debate of climate change would be important to, one, highlight how climate models in their inherent uncertainties might not be a very useful way of predicting the future, right? If hydrology depending on the given type of combination, duration, how those variabilities play together, that might be very important, and models are missing that. It could be something to highlight, right? And the other thing is this type of analysis can be used to analyze model outputs too. There's a lot of interest when you do, CMIP5 type of CMIP6 type of analysis of, people extract and aggregate annual, monthly maybe, but that's it. No one looks into interstorm variability when doing climate change, CMIP6 and type of analysis, and they might be missing a lot. So yeah, if you believe in climate change models, when you analyze them, you should take things into consideration. If you don't believe it, this is a very good example of tell you have to be really careful looking at these models. So there's opportunity for both skepticals and non-skepticals, I think.
Antonio, thanks for coming and talking with us. I was curious if you could just talk a little bit more about how vegetation might either cause these patterns to change or amplify these patterns. And I'm thinking partly, you're talking about this timing of precip affecting stream flow. We kind of expect the same thing to impact plant growth. The longer between storms, and they might take longer for those plants to recover and start growing and using water again. And so I'm just curious, if you thought more about that and where you're headed with that.
Yeah. This is definitely something, this modeling analysis is very simple to really focus on the main processes, right? If you think of a realistic plant vegetation representation, two things, right? One, the way vegetation modulates these responses might be important. Depending on a time scale of interest, I really don't know the answer. Maybe they interfere in a way that might create some biases. I would not say it will give different responses from this basic model, but definitely a certain bias in a given direction if you really think about realistically representing vegetation. This could also be used to understand a little bit better moisture supply for plants. If you think of, timescale variability, part of this rainfall becoming runoff, the rest of it becomes infiltration. So that could be interesting to see how this variability can be used to, explain vegetation variability. Which is something people
kind of try to do over the years. I've not seen something being done in this specific way, but this hydrologic variability also dictates, creates a microclimate that tells you what's gonna grow there or not. So, yeah, I would say these two things. I'm not sure if that answers your question so well.
Hi, I'm wondering if your analysis shows like hard and fast increasing storm intensity over time?
Okay, so the analysis allows us to create a climate that has these storms, and we try to understand what will happen in terms of behavior of a watershed. I think where and if it would be more like Stefan said, looking at the future climate models and what they're talking about in terms of intensification. There's definitely, at least from I don't work with climate change so much, but there's definitely consensus of storms becoming more intense and more spread apart. How widespread that is, it's hard to tell. Climate change studies like those big like simple stories. When we go in the map, it's like, oh, it's here and here. But in general, we're expecting to have storms that are more separated and more intense.
I guess not so much a question, but just I guess some thoughts on your presentation. So I'm a graduate student at the Warner College of Natural Resources. And I just wanted to say I thought it was really well presented because even though some of these concepts are a little bit foreign to me, I felt like I could follow your presentation really well. And one of the key takeaways I took from it was that it could be used a lot. So my work is focused on ecological restoration, especially like along riparian corridors. So I can see some correlation there. But from what I understood, it seems like the third series was kind of modeling what tends to be happening a lot, even in Colorado, like really intense rainfall in very short periods of time. And if I understood correctly, there's not as much water that is able to go into the soil. So a lot of it's like running off a lot more. Is that correct?
Yeah. The series number 2, yeah.
Okay.
Series number 2 would be, you're gonna have the same monthly total, but it falls in 2 storms versus it falls over 15 very drizzles, very like mild days.
I think I like that
Yeah.
comparison because like when you look at the average, it looks like it might be the same, like, oh, same sort of thing happened, we got the same amount of water. But when you get that same amount in such a short window of time, I guess it has dramatically different impacts on the landscape.
Exactly.
Do you think we could solve this problem by lining all riparian areas with large sponges?
No, I don't know. If they are in places where there will be stronger storms, maybe.
Come back to ecosystem. If you consider ecosystem, how in your model you model the AET, like the actual evapotranspiration, you have like a notion of what kind of land cover you have.
This transformation here between, there's a very simple assumption, right? We got the water in the soil and we gave it a potential evaporation, and the actual one is a linear function of how much water is in the soil. It captures some basics, but definitely not the most realistic of all times representation of actuality responding to soil moisture. But yeah, it's not for for a specific type of ecosystem for sure. There's no somatoconductance here or anything like that.
I guess this one is have you thought about applying it? It's actually here in Colorado, and we've talked about it in some of my classes, like the compounding effect of when there's a wildfire, it makes the soil like hydrophobic, so that like waxy layer. And I know in Colorado, especially like I-70, there was like major issues there because there was extreme wildfires, and I think it was the year after there was like really intense rain. That doesn't usually happen in such a short amount of time, and I know there was like mudslides. The road had to be closed. Have you thought like of applying any of this model work specifically to some of the sites in Colorado, especially where there's fire?
I haven't, but I would be surprised if someone is not doing that, you know, there might be people trying to couple a more realistic model that assumes wildfire and see how it responds to strong events. But maybe for this type of model, a bit too simple for applications with a very specific question like that, but something I would probably believe that we will see the same thing, you know, intense storms, we're generating more runoff. That example.
All right, if there's no more questions, let's thank Antonio. Thank you.